So we're going to get started on Notebook 2. And what I wanted to show is I know people were asking in chat that they were having some issues seeing some of these images that are on here, depending on how you opened up the notebook in Colab itself. You might see some issues there. One of the ways, and Richard posted a GIF of him doing it in the chat itself, so definitely take a look at it there. But what you can also do is go up here to where it has, go to File, Open Notebook. And in Open Notebook, you'll see this menu pop up here. You can click on GitHub, and then if you put the URL for this bootcamp, so you'll see that here that it says Project MONAI, MONAI Bootcamp 2021, click enter, and it'll load the notebooks that are right here. So then if I go through and I click on day 2, it will load me into day 2, and ideally you should now see the images within here. So that way, in case you're having issues seeing it, you want to see the actual images we're talking about, which you'll see some like here later in the notebook that we're referring to. You'll be able to see them as well in your notebook instead of just viewing it on the screen or having to go to the actual repo itself to look at the notebook there. So that's how I would recommend doing that. Someone else in the chat also posted a way to just mount it into your Google Drive folder. So you just clone everything into your own personal Google Drive folder and run everything from there. That should also work as a solution for viewing the images in the notebook itself in Colab. But let's go ahead and get started with this. We want to make sure if you're using Colab again, that you're setting your runtime, setting it to GPU. And then we want to make sure to start getting everything installed and running it. And so it's going to be connecting to a session. If you already have an existing session up and running, you want to make sure to terminate other ones. And so you'll see a pop-up come up and say, there's other sessions running, make sure that you go through and terminate things. So if you're using Colab, that might be an issue, but go ahead and just close off the other session from the previous notebook and then move over to this notebook, and then you should be good after that. So we'll go through, do the pip install for MONAI, just like we've been doing in the previous notebook, and we'll do in the next notebook as well, making sure we change our runtime, and now we have our GPU available. And so in this notebook, we're going to be going over MONAI datasets, caching, and networks. Like Eric already mentioned, with MONAI, a lot of the things that we try to do in MONAI try to work well with native PyTorch implementation versions. So as you'll see through here, we have our own versions of things like datasets and caching mechanisms, but usually they are working very well with the native PyTorch implementation. So you can easily integrate them into your current workflow if you already have PyTorch workflow set up. Going down a little bit, we want to cover a few different things. I think there's actually a few more here listed that are actually below, which I'll end up fixing, but we are covering all these topics that are here. I think there's just a duplicate on this list of 7 here. But really, we want to talk about datasets. What is a MONAI dataset? What sort of caching is available? And we'll have an assignment at the end that has you implement SmartCaching, which is one of the caching mechanisms that we'll briefly talk about throughout this notebook. What datasets are provided by MONAI? Stephen already alluded to this, but we'll see an example of it here in code. And then we'll talk about some of the different layers, network components that MONAI provides, and how you can utilize those layers or call out to your own network that we have and that we'll build here along in the notebook as well. So let's go ahead and get started. We're going to run this first file here, or first cell here, and this will kind of just bring everything in. You'll see our import statements here are bringing in dataset, data loaders, some of the different caching mechanisms, and our decathlon dataset that we'll talk about a little bit, and also a map transform. So what is a MONAI dataset? So a MONAI dataset is a generic dataset. It has a length property, an item property, and then an optional callable data transform. And Eric already covered transforms. So any of the transforms that we already saw, you can pass them easily into that MONAI dataset. And what we'll see here in this first cell is we're going to just instantiate some synthetic data. So it'll just be numbers there with a key called data in there that we'll use and reference throughout the different transforms here in a little bit. And then we'll call it to our MONAI dataset. And then there we'll pass the items, which is our data. And then transforms, in this case, we're passing none because we don't have any that we want to call. We just really want to see what that dataset looks like. And so we'll see the length of it is 7, and we'll see the numbers that we have in the cell there, 4, 9, 3, 7, 1, 2, and 5, printed out here below with the key of data. Again, we try to be as compatible with PyTorch as possible. So you'll see here we can call out to the PyTorch data loader, give it a batch size of 2. And if we go through and print all of those items, you'll see them printed here in batch sizes of 2. So 4, 9, 3, 7, 1, 2, and then 5 because we only have that single number left at the very end there. But this is just an easy way to integrate it if you want to use one of the MONAI datasets. Now, let's figure out how to actually put a transform into that chain, and we're actually going to implement our own custom little transform here as well. So in this case, we want to implement a square it transform. So we're going to inherit from map transform here, and we are going to call out and just do a little print statement here that says the key that we're actually going to be referring to. So in this case, it's going to be data because that's what we have up above in our synthetic data. And then we're going to call it to the key and then just square the data. So we're going to multiply it by itself, square it, and then return the value from there. So if we go through and run that, we'll very quickly see the output. So we'll see here 16, 81, 9, 49, 1, 4, and 25. So that's great. But we really want to see how can we start utilizing caching and what can we do with that data to really visualize and see how is this caching really helping us when we start to use it. And so one thing I want to point out, and I think Eric also kind of mentioned this as well a little bit, is what you're seeing here in this image is a transform chain. And so a composed transform chain, and you'll see two different sections on the left-hand side here. You'll see a green rectangle-ish sort of box around a few transforms, and then you'll see that pinkish, purplish sort of one down below on the left-hand side. You'll see arrows kind of showing where that data will go, whether it's cached or not. But the thing to really point out here is that in that green box, those are all deterministic style transforms. And it's really important that you start with those first in your transform chain if possible. Because when you start to use caching, it's going to make a big difference for what the function itself and what the caching mechanism can actually cache. So you'll see from that green box going right, we have that arrow called deterministic transforms. It'll select the data, and then it'll cache in cache 0, cache 1, ... And then when we go through and we need to pull it again, it already has access and knows how to pull that particular cache. And it'll already have the transformed versions of those images or of that data already cached and ready to go. So it doesn't have to redo those transforms every time that you're loading after each epoch. And then you have that purple pinkish sort of box, and that one is where you have your randomized non-deterministic transforms, and then your 2 tensor D at the very end as well. So what that'll do is, as you pull in and you're pulling in the data again for another run through of it, it'll pull in that already transformed deterministic transforms that are cached, and then only then apply the non-deterministic random transforms. And what that really does is help speed up the data loading section of your training loop a lot. And in some cases, it can give you a 10x or more speed up. And we'll see some experiments here in a little bit that really utilize this caching mechanism. And we also have a notebook that goes a little bit more in depth in our tutorials repo as well. But let's go ahead and get started. We want to implement another transform here. And in this case, we're going to do the same thing. We're going to square the values that we had up above. But in this case, we're going to call it slow square. And what we're going to do is add a sleep timer of 1 second to each loop as it does the transform, which means now that we have 7 data pieces, we want to call that 7 times, and we're going to square it 7 times, which means it should take roughly slightly over 7 seconds to perform this transform on our current data set. So we'll go ahead and run that. It'll instantiate the data set, pass in the items, and then we'll have our slow square transform in our data set function. Now, when we run this next cell, we're going to time it, and just as expected, it's going to take a little longer. It's going to take about 1 second. You'll see them slowly coming up, and then our wall time runtime is 7.01 seconds to run that, loading the data and transform it. And if you were to do this, say 100 times, because you're running through the data 100 times, you would increase your training loop by about 12 extra minutes just running with this data. So even though the transforms aren't particularly heavy in that it's a sleep timer here, if you do have a transform that takes 1, 2, maybe a few seconds, especially depending on the machine or GPU that you're running on, that time can really add up, especially as you run into the 50, 100, 200, maybe even 500 blocks in your training loop. So it's something that we really want to utilize. Now, we have a few different caching mechanisms in MONAI. One that we're going to talk about here is our cache data set. So we'll go and call out to our cache data set with our items and our transforms, and we'll see it start to load the data set here. And then we're going to time it. And so we're going to go through and loop through calling this data set now that we have it in a cache data set which will be an in-memory cache of the data. And you'll see here that it prints out, and we have a average and best time here, or it's the best time here of 23 per loop. And that means it's going really quickly. It's cached the first time that it loads up. After every loop, it's going to pretty much instantly be able to load that back up into the, as it calls out to it. And so we'll get a pretty low time here. We're not seeing that average of about 7 seconds. And that's really where caching is going to benefit you. And in this case, this caching data set function is putting the data in memory, but you can always have the data in memory. Sometimes the data is too big, you don't have enough RAM on your machine, you can't actually store everything in memory. And so when you want to actually manage things that are larger data sets, one of the nice things to do is to use a persistent caching mechanism instead. So we have our persistent data set, and that'll really help manage those larger data images that are not going to be able to fit into memory directly. And what we do when we call out to it, so I'll go ahead and run this one here, is we'll call out the persistent data set, pass in our items, our transforms like we did before. But in this case, we can specify a caching directory. So in this case, we have my cache as the directory. And what it'll do is it'll use the path to the actual data and then use a hash of that value for the actual file directory or where it's located at, and use that as how it stores the cache version on disk for that data. So let's go ahead and run this loop of it, time it. And we'll see again that for the first call out to it, it's going to take about 7 seconds again. But if we run it again, we'll see really quickly that it ends up being just a few milliseconds. So 19 here in this case. And that means it's already cached and it's pulling from that cache directory there. We can also see what that cache directory looks like. So we'll see that there should be 7 entries here, 1 for each data point that we had. And the name of it here is just a hashed version of the data itself. And so the nice thing about this is that this can also be, so long as the pathing stays relatively the same, it can also be moved machines because things are already transformed and written out to a cache. And so that means that it can stay relatively the same, so long as the file pathing stays the same as well. Now, if we go through and run it through and time it, so it goes through it a few times, we'll see that we'll also get a fairly low average time on it because it is pulling again from the cache already, since we've already implemented it and called it once. The kind of neat thing is if we instantiate a new version, so in this case, we call it the persistent data set, we give it the cache directory and we instantiate it into a new object, it will reutilize that already cached directory there to check that things are there. And it shouldn't take very long to be able to instantiate it and run it again, because it can reutilize that cache data and make a fresh instance of it. And so we'll see that that average time again is exactly the same as the loop above in our original instantiated version of it. I mentioned earlier that we do have our smart caching data set as well. That's going to be part of the assignment here in a little bit, but we also have a notebook that talks about the performance of some of these different caching mechanisms. And here you see 2 different graphs. And what you'll see on is that there is a red, a blue, and a green, and that's for a regular data set, a persistent cached data set, and then an in-memory cached data set. And the total train time for this is 600 epochs. And you'll see the number of seconds that it's taken overall for either a particular epoch or per epoch, depending on which graph you're looking at. But you'll see on that left-hand chart that you're almost at 60,000 seconds just for that loading of the data set and loading those images in without caching. And so in a case like this, you can save a lot of time by using one of the caching mechanisms, whether that's persistent or in-memory caching. And there's only a very slight overhead for doing that on the initial run. And then on the right-hand side, you'll see sort of a per epoch timing, which is about 100 seconds per call if you're not doing any caching. And then a pretty minimal call and time to do this if you're using one of the other caching mechanisms. And so I encourage you go and look at, we have this acceleration folder in our tutorials repo. It has information on this caching mechanism, but also a lot of other general acceleration and performance notebooks that are in there. Nick will be talking about some GPU accelerated training things later on today as well, that kind of go into some more just general acceleration and performance techniques, but caching is definitely one of the important ones. So moving down, we have a few different data sets that are provided by MONAI. I'm going to go ahead and run this because it'll take a little bit to download. You don't have to run this on your side, especially if you're running locally. If you're running in Colab, it will take just about 1.5 minutes to download. But if you're running locally, you don't have to do this. We're not going to use anything with this section. We just kind of wanted to show you how it works. But in this case, we're downloading one of the tasks from the Decathlon dataset. And Stephen mentioned it earlier in our datasets that we provide. This data is up on AWS's Open Data Initiative, hosted on AWS, and we have links to it through these functions within MONAI. And so you can specify a root directory, a task, and in this case, it's task 9, which is spleen segmentation, which section of the data you want, in this case, training, and whether you want to download it or not. And in this case, if it was already downloaded, it would double check that it's already cached on disk and that it wouldn't need to download it again. But this is a nice wrapper for pulling in that data, and then it also extends the cache data set that we saw above. So in this case, you're already getting to use some of those things that are in MONAI that really help your performance when doing these training loops. So that's about to complete here in a second. What we can see is after we pull in that data set, we can get some properties on it. So we can call out to num training and description, and we'll see the number of training images and the description for the data set. And then we can also pull in the first image and look at both the image shape and the label shape that are here. And we'll see that happen here in just a second. We also have the MedNest data set available as well. And we also have other notebooks that pull from things like the TCIA repos with other data sets that are involved. They're just not direct functions within MONAI, but we do work with a lot of different data sets and open source data initiatives. So definitely check out some of the notebooks that are in that tutorials repo on our Project MONAI GitHub. And so we see here that the data set is being loaded. It'll be just a few more seconds, and then we should be able to see the properties that we wanted to call out to here. So I'm going to give it one more second and we'll see that happen. So there we go. Number of training, 41, description, spleen segmentation, and then we have 512, 512 by 55 data shapes for the first image that's in there. So moving forward, we want to talk about networks and network components within MONAI. We have a lot of components that are available within MONAI that allow people to sort of build up from sort of low-level layers and sort of base factory methods for creating these custom layers that are really extensible based on sort of the dimensions that you pass in, the arguments and other parameters that get passed in. We have some mid-level blocks that are available as well that have these reusable concepts of within the networks and what they're constructed from. And then we also have our nets, so our fully defined networks that are available for you to use and easily implement and utilize in your own workflow. And so diving a little bit more into the blocks that are defined in MONAI, we have things like convolutions, residuals, and all the way down to subpixel convolutions. And we'll see what those look like here. And so if we unhide this block, we'll see that we can import from our MONAI networks layer, and we'll import convolution, activation, split args, and pulling. And then we'll see some examples of that, the way that we can kind of use these as passing in parameters and make them pretty adaptable and flexible for when we're actually using them. So in our case, we're going to print out calling to convolution, which takes 2 arguments. And the first argument is going to be whether it's a convolution or a transpose convolution. And then the second argument is going to be what sort of dimension do you want, 1D, 2D, or 3D. And in this case, you'll see both versions printed out in all the different dimensions. And then because these are vanilla PyTorch layers, we can also call out with parameters directly to them and instantiate them with input, output channels, and then the kernel size as well. So you'll see that we're just reutilizing those same calls from up above and calling out with parameters directly in there available. Activations don't require any spatial dimension, but they also do support additional arguments. So in this case, we can call out to one of our activation functions, and then we can pass in the parameters as well. So number of parameters here, and then the initiation as well for it. We also have the split args function. So if you want it in a tuple instead to make it a little bit more readable and make it a little bit easier to manipulate some of the parameters that are being passed in, you can also do that. Use split args to split the data correctly, and then you can pass that into the activation function as well. So if we go ahead and run that, you'll see that it has the number of parameters listed right here as we print out the output from it as well. Now, why is this helpful to have these layers set up this way? Well, we'll go ahead and create using these components, our own sort of flexible network definition. And in this case, we're going to start off with a class called MyNetwork, and it's just going to inherit from the torch modules. And we need two functions. So we need our init function, and we need our forward function defined within this class. And we'll pass in some default parameters that are up above here for dimensions, channels, outputs, kernel size, and pooling, and activation. And then you'll see that we can call out and define into our self parameter these different extensible versions of these layers. And so we'll see convolution, the type of convolution that we want, and then it's passing in all of those parameters that we pass into the class definition or the default parameters that are there. Same for activation and same for pooling. And then we have our forward pass. And so for our forward pass, we'll go through convolution, through activation, and through pooling. So if we go ahead and run that really quickly, we now have that definition of our very flexible network. Now we can run the default version of the network. So all those parameters that got passed in init will get instantiated and run through in our flexible network. And we'll see those versions down here. We'll also have a 2D version and a 3D version with different activations being passed in, different kernel sizes, different input channels and output channels. And so if we look down at the output for this, we'll see that we have the layers that we had in our forward pass, so our convolution, activation, and pooling layers with the different parameters that we passed in. And then you'll see that as we change the dimensions, it will reflect that as well here. So we have 2D version and 3D versions depending on what we passed in. And then we have a lot of other networks provided in MONAI. We have over 20 other networks, including things like UNets and VNets. But let's go ahead and implement one of those. So here we'll have an example unit. We'll define two different units. And again, because this is using that flexible implementation, we can use that same base caller, but pass in those different dimensions. And so in this case, this top one, we'll instantiate a 2D version of our unit, and it'll get defined there with our input, output, channel, and strides passed in as parameters. And then we can easily replace that and replace some of those parameters. So in this case, we replace dimension with 3, which means we'll get a 3D version of this unit. And then we can also override the default activation function that gets passed in. So you'll see here at the very end, we have an activation that will pass in, and that'll kind of replace that. And we can add these custom layers into any of these networks that we have. So if we click run, we now have the 3D unit and we have the 2D unit from up above. So very easy to utilize the default networks that are in MONAI, or to create your own version of a network that is easily extensible in this same way. One thing I want to mention, which Eric also mentioned a little bit about as well, while going through sort of the architecture diagram of MONAI, is that we also have our workflows. And so those workflows include the Ignite class engine, which we'll talk a little bit more in the next notebook. But really, that's to kind of provide a wrapper around some of the functionality that we have, and all the things that you're seeing here work well with those workflows. You can integrate into Ignite, which is a lot of the default ones that we have, or even other modules like Lightning or Catalyst. So to summarize, we talked about MONAI datasets, data loaders, cache mechanisms, and the networks that we have available. And we really wanted to highlight that there is those caching mechanisms that are there. They're very useful. And then we have options for different data sets that are already predefined within MONAI. We have tutorials out there that utilize other data sets as well. And then beginning to understand how we compose our networks. So we're going to move on to our assignment section. For our assignments, we have 2 assignments, and we'll give about a little over 5 minutes to kind of go through these, ask questions in chat. We'll check back in how people are doing in about 5 minutes. But the high level is, for the first assignment, is we want to instantiate a data set with SmartCache. So you can go ahead and use the data from up above. We're going to combine a new transform that minuses 1 from the value. And then we're going to combine it with that slow square from up above, the one that takes it adds an extra second to each of the inputs. And then we're going to instantiate our SmartCache data set with a replacement rate of 0.2, cache of 5, and then run that 5 different times just to kind of see what it looks like. So I would recommend messing with that, trying to add maybe more data to the data up above that we had in the one of the first cells, try different replacement rates, try different cache numbers, run through it, see what it looks like. And we have those functions there. And you'll see below that there are some extra functions that need to be called for SmartCache of when you actually want to do your replacement, which you'll see down below as well in our skeleton placeholder here. And then for assignment 2, we want you to instantiate a network from the MONAI library. So choose not a unit that we defined above, but go ahead and go look for one of the networks that are there in the documentation, define it, and then look at the layers. So call out to it, use torch summary or print out the model itself and look at those composable layers. That way you can start to see what it actually looks like for some of these architectures that are implemented within MONAI. So I'm going to give about 5 minutes. I'm going to go check on lecture questions that are there. We can answer some questions that we come back and go ahead and get started with the assignment. All right, I'm going to start going over the review and then we can answer any questions after that. And then I think we are scheduled for a break after this. And so let me go through and quickly go through the solution for this. So going back to assignment 1 here, we had 2 different assignments. Assignment 1, we wanted to instantiate a data set with SmartCache. And so we wanted to write a transform, a -1 transform, utilize that with the slow from up above, and then instantiate the SmartCache data set. So in this case, we'll see that we import our SmartCache data set. In our -1 transform, all we are doing is calling out to the key and minusing for 1. We're not doing any additional checking. It should be simple enough to just write it in with this way. And then we'll add that -1 into the compose function. So we have slow square and -1 in that smart transform parameter here, or the smart assignment variable here. Then we'll pass that smart transform variable into our SmartCache data set. So the way that we call out to that is we do monai.data.smartcache dataset, or we can call out to the SmartCache dataset short import up above. And then we pass in items, our transforms, just like we have for other caching data sets. And then we have 2 other ones. So replacement rate, and the way that replacement rate works in this case is that it will replace, in this case, 20% of the data that's available and that's in the actual cache itself. And then we give it a cache number. So in this case, we want to cache 5 pieces of data. So every time we call out again for it to replace the cache, it will replace at a rate of 0.2 or 20%, depending on the size of your data. And then in this case, we will keep a max of 5 data points. It's really helpful for our particular example because we only have those 7 data points. But when you're using it on an actual data set, you'll definitely want to tweak what this actually looks like. But if we go ahead and run that, you'll see the data gets called out here, and you'll see it in a particular order. So in this case, 24, 8, 80, 48, and 15. And then when we want to start utilizing SmartCache, we can call out to that caching function an object and say start, which will start the replacement mechanisms. And then whenever we want to update the cache, so you'll see here in the loop that we print out the items and then call to update cache. And this will go through, instantiate that replacement rate, and then we'll bring in the new set of data into the cache for it. And at the very end, we want to make sure to shut down that mechanism as well. But the big thing here to see is what do these look like as we print them out. So you'll see the first version is 24, 8, 80, 48, 15. And you'll see that slowly just start to slide with how much we replace it by. So then you'll see that we have 8, 80, 48, 15, which are the same from up above on this first round. But we get rid of this first 24 value and instead add a 3 to the very end of it. And that pattern will continue. So we'll reutilize these 4 values here, 80, 48, 15, and 3. And then we'll pull in 1 additional data piece here, which is 0. And that loop continues around every time that it goes through the loop and calls out to the smart caching mechanism to update the cache. This is really helpful, especially if you have a particularly large data set. I know with some of the digital pathology workflows, this is especially helpful because you can't use all of the data, or using all of the data can make things take a particularly long time. So this can use sort of a subset of data, but making sure that you're still sort of changing out the data that's in the cache and getting in new data. And then moving forward to assignment 2. In this case, we called out to a DenseNet 121 network with some of the parameters that are there, input channel, output channel, and spatial dimensions. really the big thing that we want to see from here is you'll see those layers that we talked about above. So the convolution 2D, batch norm 2D, ReLU, max pooling 2D, and you'll see that there's these blocks as well that are here. So like a dense layer, dense block that has a lot of sub layers in there as well. So these are kind of what we alluded to before. They compose a lot of the networks that are there in MONAI, and these building blocks are there to make it really easy and scalable to create these network architectures. And there are a lot of other networks that are there. We have 20 plus networks that are in MONAI, and more that come out with every release. And then kind of scrolling down, we see a lot of those different layers, a lot of utilization of those dense layers. And it's really helpful, especially when you have a network of this size. And then the other thing we wanted to see again is just sort of another one. So in this case, there is things like a UNet that we can call out to, or defining a class for a UNet, and then extending this for the classes as well. So you can do override methods for things, call and then call back out to it with parameters. And in this case, we print out that UNet and we see these layers again. So we see these convolution layers that we have. And again, reutilizing those layers that we have and the blocks that we have available within MONAI to help you build those networks. So next, we're going to take a break here for about 10 minutes or so. Go ahead and get up, stretch, get some coffee, get some water, go to the restroom. We'll meet back here at about 10 a.m. PST, or at about 8 to 10 minutes. We'll probably wait a little longer, maybe 10:02. Make sure people have at least 10 minutes to go through and stretch. We'll come back and I'll look at some of the questions that were here in the lecture questions. We can start off with answering a few of those in case we missed any that are really important, and then we'll get started into our next notebook. So go ahead, take a break, and we'll be back here in about 10 minutes or so.